Hello everyone, welcome back to my channel. In our today's video, we will be taking a very important topic, that is quantum numbers. We will be trying to understand the basics of quantum number and what is the significance of each quantum number and their relationship. Also, we'll be trying to take the shapes of different orbitals in this particular video. We'll try to see that what are the shapes of different orbitals. So let us start with the quantum numbers. So remember that quantum numbers works like an address for an electron. Okay, it helps us to identify and kind of locate electrons in a multi-electron system. So in multi-electron system, to identify an electron, we use this quantum numbers. So there are altogether 4 quantum numbers, and each quantum number specify a specific or has a specific significance. So whenever you talk about quantum numbers, okay, so how we can understand it in a very simple way. Try to understand that whenever you want to get an address, whenever you give an address, okay, so what basically you do is to narrow down the intended recipient, right? To actually to let anyone know that where you stay, what you do. Basically, you give the state in which you are, the city where you are right now, the street, and the house number. So if anyone wants to find out that where you are, or if you want anyone to find you, so basically what you do is you give this 4 things, that is the state, then the city, then the street, and the house number. So using this, anyone can find you. In the very same way, whenever we talk about a particular electron, okay, the quantum numbers works in the very same way, okay. So the 4 quantum number actually specify 4 things which help us to localize or to identify a particular electron. So that is first energy level, which is given by principal quantum number. Then we have the subshell, which is given by azimuthal quantum number. Then the orientation of the orbital, which is given by magnetic quantum number. And finally, the spin of the electron. So these 4 things are required to specify and identify a particular electron in a multi-electron system. So whenever in an atom you have many electrons, to specify a particular electron, we need these 4 things. That is energy level, to which energy level that particular electron belongs, to which subshell, to which actually orbital, and what is the spin of that particular electron in that particular orbital. So to find out these 4 things, we require the 4 quantum numbers. So the importance of 4 quantum numbers is each one of them specify this particular one will specify the energy level, the another one will specify the subshell, the another one will specify the orientation of orbital, and finally the last one will specify the spin of electrons. Okay, so let us try to see what are those different quantum numbers. But always remember that if anyone will ask you that what are quantum numbers, obviously there are no doubt that they are actually they help us to localize or identify a particular electron. But always remember that quantum numbers are solution of Schrödinger wave equation. Okay, so the solution of Schrödinger wave equation provides us 3 numbers, okay, which specify the energy, the shape, the size, and the orientation of large number of orbital present in an atom. Okay, these are nothing but quantum numbers. And try to understand that we are always saying that there are 3 numbers. So remember that when we solve Schrödinger wave equation, we get 3 quantum numbers, not the 4. Okay, but we have 4 quantum numbers. The last quantum number, which we called as the spin quantum number, is not a solution of Schrödinger wave equation. So if anyone will ask you that what are quantum numbers, obviously quantum number help us to specify the position or the location of an electron, no doubt, or to specify or identify an electron, no doubt in that. But to be very specific, they are solution of Schrödinger wave equation. Okay. And remember that the three quantum numbers which we get as a solution of Schrödinger wave equation are principal quantum number, azimuthal quantum number, magnetic quantum number. So these are the three. As I have told you, there are four quantum numbers. So to specify, to completely specify an electron in an atom, a fourth quantum number called spin quantum number was introduced. Okay, so that was later incorporated in it. It is not a solution of Schrödinger wave equation. So if anyone will ask you, the four quantum numbers, all the four quantum numbers are not solution of Schrödinger wave equation. Okay, only the first three are the solution of Schrödinger wave equation. The last one is not. Okay. Then let us try to see the significance of each quantum numbers. Okay. The first one is the principal quantum number. So what is the importance of principal quantum number? What it tells us? Remember that it was proposed by Bohr. Okay. If you happen to actually understand what is Bohr model of atom, in Bohr model of atom, Bohr specified the energy level as n equal to 1, n equal to 2. So as we go higher into the energy levels or the orbit, then the number goes on increasing, right? It was denoted or it was given as n equal to 1, 2, 3, 4. It goes on into the higher orbits. Okay. So remember that those numbers are nothing but the principal quantum number which was proposed by Bohr. So if you haven't watched those particular videos on Bohr model of atom, do watch the video on Bohr model of atom first so that you can understand that what is actually or how Bohr gave this particular quantum number. Okay. The value of principal quantum number can be any integer with a positive value that is equal to or greater than 1. So it can be any positive value which is greater than 1. So it can be 1, 2, 3, 4. It can just go on. It determines the average distance between the electron and the nucleus, means it denotes the size of an atom. So remember that the importance of principal quantum number is it gives us the size of an atom. Obviously, if anyone will tell us that the principal quantum number for this particular atom is 1 or 2 or 3, okay, so what basically we can get is an idea that we are going away from it often, actually from the nucleus, and that electron is how much far from the nucleus, we can easily find it out. Okay, so as anyone say n equal to 1 and n equal to 2, so obviously n equal to 2 is farther away from n equal to 1. So if I'll say n equal to 3 and n equal to 4, so obviously n equal to 3 will be far away from n equal to 2. So as you go on increasing the principal quantum number, the size of an atom will also goes on increasing. So it determines the average distance between the electron and the nucleus. It determines the energy of an electron in an orbit. Okay, so it tells us about the energy of an electron in an orbit where the electron is present. If you actually understand Bohr model of atom, in Bohr model of atom, Bohr has told that whenever we go higher into the orbit, obviously the energy of the electron in that particular orbit will go on increasing. So as you are in n equal to 1, and let's say if you happen to go to n equal to 2 or n equal to 3, as you go into higher into the orbit, the energy goes on increasing. So it also helps us to determine the energy of an electron in an orbit. Okay, it tells us that, okay, which electron will have higher energy and which electron in a particular orbit will have lower energy. It can tell us that which shell is actually bigger, which shell is smaller. That means it can tell us about the average size of an atom also. The maximum number of electron, always remember that in an atom is represented by this quantum number, and we always write 2n square. Okay, like in the first orbit, if I put n equal to 1, so the maximum number of electron which this particular orbit can take is 2 into 1 square, which will be 2. Like if it is the second orbit, it will be 2 into 2 square. So it will be 2 into 4, which will be 8. So that is how it can tell us that in which particular orbit, how many maximum electron we can take. And the formula is 2n square. It gives us the information of the orbit. That's what, as if you actually happen to go through the Bohr theory, then you will understand that the Bohr theory has designated the particular orbit with the symbols that is K, L, M, N. So that means if I say n equal to 1, it means the K shell. If I say n equal to 2, it means the L shell. If I say n equal to 3, it means the M shell, and it can just go on. Okay, something like this. Okay, so if you can understand over here, okay, so whenever we talk about the principal quantum number, okay, so this is n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. Okay, it can just go on. Okay, K, L, M, N, O. You can clearly see that the energy is E1, E2, E3, E4, E5. It can just go on increasing. And this number is nothing but principal quantum number. Okay, and as we have learned in Bohr theory also, this energy or this particular orbits are also known as stationary states. And remember that if you go on increasing, if you go higher into the orbit, then what will happen is the energy will go on increasing. So it will be E1 will be less than E2, then less than E3, then E4, then E5. So E5 will have the highest energy. It can just go on increasing. So that is what actually, or these are the informations which we get from the principal quantum number. Okay, so the importance of principal quantum number is it tells us about the principal shell to which an electron belongs. If n equal to 1, that means the electron belongs to first shell. If n is equal to 2, that means the electron belongs to second shell. If n is equal to 3, it belongs to the third shell. So it can just go on. It tells us about the size of an atom also, like if n equal to 2. If a particular atom has 2 shells and if a particular atom has 3 shells, obviously the atom having n equal to 3, that means 3 shells will be bigger than n equal to 2. It can tell us about the average energy of the electron in an atom also, like if a particular electron is present in the first shell and if a particular electron is present in fifth shell, so obviously the fifth shell will be higher than the first shell, or the third one will be higher than the second one. So it tells us about the average energy of the various electrons in an atom also. Okay. Then coming for the next, okay, that is the azimuthal quantum number. So this azimuthal quantum number actually gives us the subshell in which the electron is present. It is also known as angular momentum quantum number. And remember that it was proposed by Sommerfeld and denoted by L, okay, small l. It determines the number of subshell or sublevels to which an electron belongs. So how many number of subshell is present in a definite energy level and to which subshell an electron belongs, that is what actually is given by the azimuthal quantum number. It tells us about this shape of the subshells. We'll be coming into that as we finish this quantum number. We'll try to see that what are the different shapes of the subshells. That is also given by the azimuthal quantum number. It also expresses the energy of the subshell. Okay, means which subshell is lower energy, which subshell is higher energy, that is also given by the azimuthal quantum number. The value of L, so that is the relationship between L and N. Okay, so if you want to get the value of L, then L will always be equal to 0 to n minus 1. So that is the relationship. For example, if I'll give you n is equal to 4, and if I'll ask you what are the values of L, so if n is equal to 4, L can have 0 to 4 minus 1. 4 minus 1 means 0 to 3. So what are the values of L? 0, 1, 2, 3. That is how it goes. So if someone will tell you L is equal to 2, so it will go from 0 to 2 minus 1. So it will be 0 to 1. That means 0 and 1. So remember that is the relationship between L and N. So for a definite value of N, you will have some values of L. So if anyone will give you the value of N, you can find out how many subshell are present in that particular energy level. Okay, so that is how we can know that in which subshell, how many, or in which shell, how many subshells are present. Like if anyone will give me third shell, then the subshells are present are 0, 1, 2. Okay, if anyone will give me fifth shell, the number of actually subshell or the subshells which are present is 0, 1, 2, 3, 4. If anyone will give me n equal to 4, it is 0, 1, 2, 3. It has to end in n minus 1. Okay, so that is how actually we can find out how many subshells are present in a definite energy level. And remember that once we get that value of L, let's say if you get value of L as 0 or 1 or 2 or 3, they are designated by a symbol. Okay, like 0 is always known as S, 1 is always known as P, 2 is always known as D, and 3 is always known as F. Okay, so if, let's say, if I give you for an example, if N is equal to 2, what are the values of L? So you'll write 0 to n minus 1. So it will be 0, 1, right? That if L is equal to 2, so it will be 0 to n minus 1. So 0 to 2 minus 1. So it will be 0 to 1. So it will be 0, comma 1. So there are two values of L. So 0 and 1. So what is 0 and 1? That is S and P. So in energy level 2, what are the subshell present? S and P subshell. Let's say if anyone will give you n is equal to 3. The principal quantum number is 3. What are the subshell present? 3 means it will be 0 to 3 minus 1. So 0 to 2. So it will be 0, 1 and 2. So what are the subshell present in n equal to 3? That means in the third shell, it will be S, P and D. So that is how actually we can find the subshell in various shells. Okay, and remember that each subshell will have a definite shape. Like S subshell will have spherical, P will have dumbbell, D will have double dumbbell, and F will have complex. So the shape of this particular subshell I'll try to show you at the end of this particular video. Okay, now coming for the third quantum number, that is what we call as magnetic quantum number. So what is the importance of magnetic quantum number? Remember that it was proposed by Zeeman, okay, and is denoted by M. Okay, it gives us the number of permitted orientation of subshells. Okay, so how many orientation of the subshells are there? That is actually given by this particular quantum number. In very simple words, it will give you the number of orbitals, okay, in a particular subshell. And the value of M varies from minus L to plus L through 0. So always remember that. That is the range. So if anyone will tell you that, let's say L is equal to 2, how many or what are the values of M? So if they say L is equal to 2, so it will go from minus 2 to plus 2. So you have to count it. Minus 2, plus 1, 0, plus 1, plus 2. So there will be 5 values. If anyone will tell L is equal to 1, how many value of M it will have? It will be minus 1, 0, plus 1. So 3 values. So that is how actually we can find out how many values of M. That means how many orbitals are present in a definite subshell. That is nothing but the number of permitted orientation of the subshell. For a given value of n, the total number of m is equal to n square. So remember that if anyone will give you the value of n, that means the principal quantum number, and they ask you how many values of m will be there, it will always be n square. Like if I'll ask you in second shell how many, or let's say let's say second shell how many values of m will be there, then you can easily find it out with the help of that how many orbitals are present in that particular shell. Okay, you can just put n square, the value of n. Okay, so whatever value of n I'll give you, the total number of orbitals in that particular subshell is in that particular shell is given by n square. Okay, for a given value of L, the total value of M is equal to 2L plus 1. So that is what it ranges from minus L to plus L. So the total value which you will get will always be equal to 2L plus 1. So that is the relationship between L and M. And the range will always be this only, minus L to plus L through 0. Okay. So here are actually the, you can see as a summary, okay, if I'll just try to make you understand, you can see there n is equal to 1, okay. For n is equal to 1, L can be 0. I hope you can understand that, because for n, L is nothing but 0 to n minus 1. Okay. So n minus 1 will be what? 1 minus 1, which will be 0. So for n is equal to 1, L will always be equal to 0. So for L equal to 0, what is the value of M? Because L, for any value of L, M ranges from minus L to plus L. For 0 will not have minus 0 or plus 0. So if L is 0, M will be equal to 0. So how do we designate the orbitals? The designation of orbital is done as 1s. Why 1s? 1 represent the principal quantum number, this 1, and L equal to 0 means s. So when we write 1s, 1 stands for principal quantum number, s stands for azimuthal quantum number, that is for 0. And how many number of orbitals in the subshell? Obviously 1. Then n is equal to 2. For n is equal to 2, what will be the value of L? So for n equal to 2, the value of L will be 0 to 1. I hope you can understand, because the value of L for any value of n will be 0 to n minus 1. So 2 minus 1 will be 1. So it will be 0 to 1. So see, both are 2. For 2, you can have 0. For 2, you can have 1. So for L equal to 0, what will be the value of M? Obviously 0. What will be the designation? 2s, because for L equal to 0, we write 2s. Number of orbital 1. Now, 2. Can you see that this is 1, right? For M, L ranges for L equal to, for any value of L, M ranges from minus L to plus L. So what is the value of L? 1. So it will be minus 1 to plus 1. So minus 1, 0, plus 1. So how many orbitals are there? See, there are 3 values. That's what I have told you. The value of M gives you the orientation of the subshell, which basically means the number of orbitals. So how many orbitals? How many values are there? 3. So you will have 3 orbitals. Okay, that is what we say as p orbitals are of 3 kinds. Huh? So that is how actually we get it. So what is the designation of this particular orbital? It is present in the second shell. So 2, and L equal to 1 means p. So 2p. Similarly, you can see for the others also it is actually solved in the very similar manner. So you can just have a look that for 3, it will be 0, 1, and 2, because it ranges from 0 to n minus 1. So n minus 1 is 3 minus 1, which is 2. So 0, 1, 2. For 0, it will be 0. For 1, it will be minus 1, 0, plus 1. For 2, it will be minus 2, minus 1, 0, plus 1, plus 2. So total number of orbital for D will be 5. Similarly, for F, you will get a 7. Okay, so you can just go through that. I hope you'll understand that. Okay, then coming for the next, that is the spin quantum number. So as I have told you, these 3 quantum numbers are the solution of Schrödinger wave equation. Okay, but remember that the spin quantum number, to completely specify the or to identify a particular electron in a multi-electron system, this 4th quantum number was introduced later. Okay, and was incorporated, and it's not a solution of Schrödinger wave equation. Okay, it was proposed by Goldsmith and Uhlenbach and denoted by a symbol S. Okay, the value of S is plus half or minus half, which signifies the spin of or rotation or direction of electron on its axis during the movement. Always remember that the electron moves in its own axis, okay, and it rotates in 2 different directions, either clockwise or anti-clockwise. If the electron in an orbital is rotating clockwise, we actually designate it with a plus half. And if it is minus half, that means it is rotating anti-clockwise. And always remember that in an orbital, we can put at the maximum of only 2 electrons. Okay, so 1 electron, if it is plus half, the other must be minus half. The spin may be clockwise or anti-clockwise. That is what I have told you. Okay, so if it is plus half, it is clockwise. If it is minus half, it is anti-clockwise. This quantum number is not the result of the solution of Schrödinger wave equation as solved for hydrogen atom. So remember that it is not a solution of Schrödinger wave equation. The first 3 is the solution of Schrödinger wave equation. This is not a part of the solution of Schrödinger wave equation. So that is how actually we can understand that how to specify the or how to identify a particular electron in a multi-electron system. So there are 4 things which you must have, or 4 numbers, that is principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. Principal quantum number gives you the number of shell or which shell the electron is present. Azimuthal quantum number specify that which subshell the electron is located. Magnetic quantum number specifies that which orbital the electron is present, and the spin quantum number specifies the spin, whether it is rotating clockwise or anti-clockwise in a particular orbital. So these are the 4 things which we require to specify the or to identify a particular electron in a multi-electron system. Okay. Now coming for the next, that is the shapes of orbital, as I have told you. Okay. So shape of s orbital. Okay, so for s orbital, L is equal to 0. I have told you. So for L equal to 0, L will be equal to 0. Okay, so for L equal to 0, if M is equal to 0, so s orbital have only one unidirectional orientation. Okay, so if it will have only one unidirectional orientation, that means s orbital will have s orbital will be of only one type. That is what we are trying to say. So that will be the shape of s orbital. Okay, it will be spherical shape. So you can clearly see in this screen. So whenever anyone will ask you what is the shape of s orbital, it is spherical. And why do we have only one type of s orbital? Because for s orbital, the value of azimuthal quantum number is 0. So for L equal to 0, M is always equal to 0. And M equal to 0, that means it has only one type of orbital, only one value of M. Okay. And depending upon the value of m, we have different types of orbital. So value of m decides how many orbital a particular subshell has. Coming for the p orbital, for p, L is equal to 1. So m can be, m ranges from +1 to -1. So how many values? 3. So how many types of p orbital you have? You have 3 types of p orbital. That means the orientation of p subshell is in 3 direction. You have 3 orientation, and that is designated as px, py, and pz. Okay, which you can see in the screen. So that is the shapes of the p orbital. Okay, px, py, and pz. So basically, when we say px, it is known as a dumbbell shape. You can see it is in the x-axis. Py, it is in the y-axis, and pz, it is in the z-axis. Okay. Then coming for the shape of d orbital. Okay, we know that for d orbital, L is equal to 2. So what will be the range of m? M ranges from -L to +L. So it will be -2, -1, 0, +1, and +2. So how many types of d orbital you'll have? You'll have 5 types of d orbital. What are they? They are designated as dxy, dyz, dxz, dx square minus y square, and dz square. Okay, that is the designation which we use. If we try to draw the shape, remember that d orbitals are double dumbbell in shape. Okay, so this is dxy. Okay, 2 dumbbell shape. You can clearly see 2 dumbbell shape orbitals. Okay, double dumbbell in between the axis x and y, dzx in between the orbit, in between the axis z and x, dyz in between the axis, that is y and z, dx square minus y square, it is in lying in the axis. You can clearly see in x and y axis, and dz square, okay, which you can see is lying in the z axis. Okay, and you can see over there is a circular actually shape also that is very much to draw. That is also the region of space where we can find the electron. That is also a part of the orbitals. Okay, so that is how actually we can understand that why d orbitals are of 5 kinds, why p orbitals are of 3 kinds, or why s orbital is of 1 kind. Okay, and what are their different shape, and what are quantum numbers, what is the importance of quantum numbers. So the basic importance of quantum number is it works like an address of an electron, which specify that in which shell, in which subshell, in which orbital, and what is the spin of a particular electron which we want to identify or specify. That is how actually we can understand what are quantum numbers and the importance of it, along with the shapes of orbital. So thank you, everyone. Do subscribe for this channel for explanation on various topics in chemistry. So thank you, everyone.